Hello, class. So today what we're going to be going over is basic parameter estimation, reverse mode AD, and inverse problems, right? So this is where we'll start to connect back with what we were looking at with the physics-informed neural networks. The physics-informed neural networks were, if you think about what the model actually is, the model is just a neural network. And then we set up differential equations in such a way that they could be used as a form of regularization to be able to bring in physical knowledge to the training process, right? But then from there, what we've done is we've really built up this whole theory of how do what are dynamical systems? How do you simulate these scientific models in ODE solvers? How do you handle stiffness to forward mode AD for these stiff Jacobians that show up in these equations, right? So we did this whole thing on how do you actually simulate these really difficult physical equations, which generally show up, right? So we know the neural network way of looking at it, and then we also know this. Then we also know how do people actually do the high performance simulations in day-to-day usage, right? And so this is the point where we'll start to connect them, right? So now we can start to ask the question of, well, if I have a full scientific simulator, can I use that instead of the neural network as my model and somehow make this compose or work in the same way as neural network training, right? And what we'll see here is that parameter estimation is basically equivalent to neural network training, and there's this relationship between reverse mode AD and backpropagation that we need to start making use of in order to do this effectively. So, so what we'll be going through in this lecture will be about how do you start to make that connection, right? So the next lecture will be the one that will specifically go into what is backpropagation of an ODE system and how do you do backpropagation of an ODE system. And your homework 3 will actually be to basically implement from scratch the backpropagation of the ODE system to be able to train a neural ODE. So you'll get a lot of exposure on exactly how this all comes together. What this lecture is, though, is it's kind of like a setup that this more at a more higher theory level of trying to explain what is reverse mode AD in comparison to forward mode AD that we were looking at before, and how does this why is this something that is well suited for parameter estimation? Why can't we just use forward mode AD? And how do you actually do parameter estimation? Right. So the first thing that needs to be described is what is parameter estimation. So let's say you have some model, f of p gives you a u, right? So you put in parameters and out comes some kind of solution from the model, right? So one way to think about this is like it's your differential equation solver, right? So your differential equation has some parameters, like what are the reaction rates? When you specify those reaction rates, if you've already specified what your differential equation is, what your initial condition is, your program will spit out what the points, what the concentrations of the drug are at different points in time, given that parameter, right? When you change the parameter around, you can have different metabolism rates. When you change the parameters around, you can have different heat flow rates. When you change the parameters around, you can have different, every physical system has some set of parameters, right? So this is an abstraction where we're now saying a part of F is the initial condition, the ODE that we've defined, like all those things are kind of enclosed into F. And now we just think about it as parameters come in and differential equation solution comes out. And so what we want to do on this kind of function is we want to choose p such that u best fits the data, right? So if we have data for a time series, we want to find the p that makes us that way we best match that time series data. Um, this is known, the basic method for doing this, right? The basic method for doing this, which keeps f intact as a black box, is called the shooting method. This is not, this is not the only method. There are ways to kind of open up the black box. So if you know that it's an ODE, you can do some very specific things. Well, and we'll be describing some of those in the next lecture. But if you want to treat this as a black box, you say, f is something that takes in parameters and it spits out u. What we need to do is we just need to call that black box with different parameters. And if we call it with the right parameters, then we will have found the best one, right? So the way that you do this is you take a cost function. So here we're going to call that cost function C of P. And that cost function is basically how bad are my current parameters, right? Now think about doing this like, the shooting method, its name comes from, shooting a catapult, or setting up a robot that throw a set of darts, right? So let's think about this robot, right? So what we're essentially doing is we say we want to hit the bullseye. And so we choose a set of parameters, and for how the robot, like all the electricity in the given parts, and then we say, okay, robot, go. And it throws a dart, it hits somewhere on the dartboard, and then how good did we do? Well, we measure the distance from where the dart landed to where from the bullseye, and then we say this is the cost associated with it, right? So the cost is not directly on the parameters. We're not saying, what is the distance of the parameters from some known value or something, right? There's this nonlinear transformation of stick the parameters into the robot, let it do its thing, and then measure how far the output actually is from the result. And this is what's captured in the equation right here, right? So the most basic one is to say, let's say we have this simulation, you stick your parameters in it, you let it take its shot, and then you check the distance against your data or your desired point y, and you use that distance as your cost, right? So using the Euclidean distance is a very common one. An example of this in practice is exactly what you're doing in your homework, right? You want the parameters of the lockable model to be correct such that you'll fit the data. Well, what you need to optimize is you need to define a cost function such like as this one, and then say, well, when the cost is equal to 0, then I will have found the parameters that exactly go through the data. And this is something that is a positive function, right? It's a sum of squares, and so it always has to be positive. And so if I try to minimize this function, then I will have found the best fitting parameters, right? So really what this does is it says, I have this arbitrary program f. If it's f of p, I define this cost function to get c of p on top of my program. And if I can find the minimum of this function, which is a scalar function, right? So we have a whole vector of parameters go in. We compute a giant array of ODE solutions over a time series, and then we find this cost function that collapses that all down to a scalar. And so C of P is something that takes an array of P's and spits out a scalar. And then what we want to know is give me the inputs P such that the scalar output is as small as possible. So why do we have to put it into this kind of scalar world? Well, because we need to have an ordering, right? You need it to be a real number because you have to have an ordering in order to find the minimum, right? Um, if you have like a complex number, then you can't always say A is less than B. So what we've really done is we've set up this problem so that way it's like parameters go in, a bad score comes out, and the bad scores are in a space, real numbers, where A is less than B is always defined. Find the inputs that gives you the smallest output. And now this is a well-defined mathematical problem where when we solve it, hopefully what comes out are parameters that give us a simulator that makes the data go through, or the line go through the data. And so this just becomes optimization, right? So there's many different ways to be able to do nonlinear optimization. I point to a few packages here: Jump, Optim, NLOpt. There's a whole ecosystem and a whole theory of nonlinear optimization. But I want to just kind of go over broad strokes and kind of give you like what the basics are of how this kind of works. And so generally there are two sets of methods. There are local methods and there are global methods. So local methods, what they do is they try to, they require that you give a point to start from, and they try to find the closest point, which is an extrema. What is an extrema? It's the point where the gradient of the cost function equals 0. Why do you want to find the gradient where the cost function equals 0? Well, because remember from calculus that your extrema, right, your maximum and minimum are going to be at points where the gradient is 0. And so, so when the derivative is 0, then you either have a maximum, a minimum, or a stable point. And so what these methods are trying to do is they're just trying to find what is the closest point to where the gradient is 0, and hopefully that's going to be your maximum or minimum, right? They try to guide it towards being a minimum instead of a maximum by going downwards in the slope, right? But essentially that's what it's doing. It's looking for an extrema, and that's what it's then going to try to spit out as the optimal point, right? Given this introduction, you can probably see that there's some issues that can run into, right? There are extrema which have a gradient equals 0, or there are points where gradients equal 0, which are not necessarily an extrema, right? So, for example, saddle points, where you have, the gradient in some, like you can have these points like x cubed, right, has a derivative equals 0 in the middle there, right? There's a true 0 in x cubed, but that's not extrema, right? It's just like it just hit derivative equals 0, because the extrema for x cubed are infinity and minus infinity. It's just that the points where you have gradient equals 0 inside the domain is at the midpoint 0, but that's a saddle point, right? There are these points called saddle points, which are not necessarily extrema, which have this property of gradient equals 0, and so local optimizers sometimes find those. The other thing that you can run into, right, is if you think of like a loopy function, like if you have three hills, um, what this thing will do is it'll put you at the bottom of a hill, right? But that might not necessarily be the bottom of the lowest hill, right? Like it's not necessarily the lowest point, but it is a point that is an optima. And so it'll find a local optima, but not necessarily the global optima. So it'll find parameters which give you locally, if you're to move your parameters around, you'll think that this is the lowest cost function you can have, or the best fit to your data you can have, but it's not globally. Like there could be a completely different parameter way over in the middle of nowhere, which is actually better. It's just you have to go over a hump in order to get there. So local optimizers tend to have a bit of issues, and so there's this whole other field of global optimization, which attempts to basically find the minimum over the entire space. The global methods are extremely difficult, though, right? Because they can't necessarily use calculus. You can always come up with weird counterexamples, right? Because you can define a function which is completely flat, and then at one point in space, you very narrowly drop down to being like almost minus infinity, and then you're just like, can the program find these 5 floating point numbers which are not 0, right? There are some extreme counterexamples you can always give to a global optimizer, and so they generally use a lot of heuristics because they have to like assume some things about your function. They have to do a whole lot of computational expense because they have to try a whole bunch of points in space, and so they're generally very computationally difficult and very problem specific. Um, so, in a lot of differential equation parameter estimation, you do need to use global optimizers, and it's something that is a very key topic in this field. But for now, we're just going to look at local optimizers, mostly because of their relationship to neural networks. So neural networks have this very interesting property that if you do local optimization, you will find a local extrema, but if the neural network is large enough, that local extrema will actually be very similar in the neural network's input-output behavior to the global optima. Like in some sense, all the local extrema converge. There's some really nice papers out there on this kind of theory, and it kind of shows that local optimization is okay with neural networks. And so since we're going to be doing a lot with neural networks inside of the differential equation, especially with the neural ordinary differential equation, we're going to focus on local optimization here. But I just wanted to make note of the fact that there's this whole other optimization literature, which is heavily used in differential equation parameter estimation, which we will not be covering in much depth right now. I think that if there's time, there could be a later lecture which will go into this. So the key to local optimizers, right, is you want to find an extrema. You're trying to find where the gradient is going to be equal to 0, and so you use the gradient inside of your computations, right? So the easiest method is just to do gradient descent, where you say, here I am on a hill. Let me check my current gradient, and let me just move in the direction where the gradient's decreasing. And if you keep on doing that, you should hit a minimum sooner or later, right? Like if you stand on a hill and then you just go, which way is pointing down? This way is pointing down, so let's move in that direction. Move in that direction. Move. If you just keep on going in the way that's pointing down, you're going to hit a minimum. And that's the theory behind the gradient descent, right? It's trying to choose a direction by using the gradient, because by definition, it's always pointing in the maximal descent direction. And then you have a learning rate alpha, which is, well, how big of a step do you want to take in that direction, right? Because the gradient tells you the direction, but you need a scalar to tell you what the magnitude of the step should be. So So this is the gradient descent method where you say, I have my current parameters pi, and I take a shot, right? Like so I throw it into my simulator. I put it into the cost function, but I don't calculate just like the cost. I use this whole simulator to be able to calculate the gradient of the cost with respect to p. And then from that tells me what direction I should be changing if I want to decrease my cost. I use alpha to be able to magnify the vector in that direction, and I take a step, right? So if you think about it, we're nesting a few things, right? Like at the highest level, we are doing, iterate over the parameters p, I, to by gradient descent. And then what are we doing below that? Well, we are, solving an ODE by iterating over time, right? T with parameters pi, right? And how do we solve the ODE? Well, inside of solving the ODE, we're solving nonlinear systems by Newton's method. And then how do we solve the Newton's method? Well, sometimes we're doing an iterative linear solve by Krylov subspace methods, right? Right, so these three steps were what we discussed in that last lecture, right? That what's going on in an ODE solve is you iterate over time, which is iterating over a nonlinear solve, which is iterating over a linear solve, and now we're sticking an iteration on top of that, right? We take this whole computational stack, which takes in parameters and spits out a solution to the differential equation, and now what we do is we put in a set of parameters, we run the whole process, we get an output. We then check, we calculate the gradient of this whole simulation with respect to parameters. It'll tell us how we should change the parameters. Then we do this again. Then we do this again, right? How do we calculate the gradient? Well, one thing that you can think of right now is you can use finite differencing, or you could use forward mode AD, right? You can say that now I'm going to make my parameters be dual numbers, right? So with different derivatives in different directions than what you're using for the Jacobians, and so I'm going to do both differentiations simultaneously. So I'm going to differentiate through all of these steps, and then what I get out is a gradient, which I then change p, and then go so on and so forth, right? So we're now nesting a whole bunch of layers in here, and this is why this is such a huge field, right? Some people in the field of numerical linear algebra specifically work on this step, right? Like how do you solve these portions better? People in the ODE field work directly on this step. How do you solve the ODE by taking less steps? And then there are people who work in nonlinear optimization, which is how do I best do this step? And when you plug all these programs together, this is when you start to have this parameter inference kind of framework, right? But the core on the top here is really just a loop where we just, you just keep on trying different parameters inside of your simulator, and each time you're calculating the gradient of your simulator results with respect to the parameters. So but you're not doing it directly on the simulator though, right? You're doing it on the cost function. But what I'm going to show you here in a second is that calculating the gradient of the cost function is essentially just calculating the gradient of the ODE solver or whatever simulator you have, right? So just to kind of get a bigger overview before we go into that detail, there are other ways to do local optimization. One nice way to do this is to say, well, we want to find the point where dCdP equals 0, right? Do we have a method that's able to find zeros of equations? I mean, from your homework and from the last lecture, from so many different things, right? You know that a way to find a zero is Newton's method. So here what you can do is you can say, like, let's use Newton's method to find the point where dCdP equals 0. Right, so let's write down what Newton's method would look like in this case. Right, we're trying to optimize parameters, and so we'd say from our current parameters, we would use the Jacobian of dCdP, we would invert it, and then we'd calculate dCdP, and this would give us our next set of parameters, right? So this is Newton's method on the equation. This is Newton's method. So if we have dc, right? So we have some function c of p equals ... right? And now what we want to do is we want to find, dc dp equals to 0. So remember that Newton's method is this process like xn plus 1 equals xn minus, let me write this down here. So Newton's method is generally g of x equals 0 is what we're looking for. And so we do this process, right? So g prime, right? This is another notation for the Jacobian. So g prime of xn inverse, right? So the inverse of the Jacobian multiplied by g of xn. This is what you'd calculate, and then you'd do the step like this, right? So this is Newton's method on a general equation g of x equals 0. So now what we want to do is we want to do that process on dc dp equals 0, right? Because we want to find where the gradient of this function equals 0. So let's plug in dc dp as the function for g, right? And when we rewrite that, what we get is the ith parameter set is going to be equal to, you take the ith parameters and then you take the Jacobian. So you take the Jacobian ddp of dc dp, and you invert that, and then you take a calculation of dc dp, right? Because dc dp is this g function that we want to find the 0 of. But what is the derivative? What is the Jacobian of the gradient? Well, if you work it out, right? So if you right, so the function, f fraction dc dp is this function, right? That outputs this vector. Well, so okay, we'll be seeing throughout this lecture that even though you've been taught your whole life that your gradient is a column vector, it is actually a row vector. And I'm going to write it down as a row vector. Just get used to it, and you'll see by the end of this lecture that you'll be convinced that it's actually a row vector. So I'm going to just start using it as a row vector right now before I even describe why that should be the case. All right, so dCdP as the gradient is actually going to be written as a partial c partial p1, L dots fraction partial c partial pn, right? So this right here, the gradient itself is a function which, it's a function which takes in parameters, and it defines 4 different functions here. And that, so it is if we can think about this as as a vector function, which is, we can think about this as a vector function which is like partial. We haven't used f today, so we'll say f1, or we could say that this is f1 of p through fn of p, right? So these are actually just n different functions, right? So since this is it has a vector input and a vector, the gradient has a vector input and a vector output. This means we can define the Jacobian on it, which means that fraction of ddp of fraction dc dp, the Jacobian of the gradient is going to be this this matrix, right? Where I'm going to just start writing down a few of the values so that we could see it. It's going to be this point where you do, right? So this is going to be df1, whenever I'm writing these Jacobians, they should actually be partials. I've just kind of gotten lazy in the last lecture, sorry. So it's partial f1, partial p1, and dot dot dot. But what is f1, right? So f1 is going to be this dCdP1. Right, so you can actually see then that this is that this matrix is going to be the matrix of second derivatives. So this is going to be the matrix which is dc squared of, or dc d squared d of p dp squared, right? This is how you normally write this. dp1 squared, right? And so then you have all of these terms along the diagonal, and then on the off diagonal you're going to have the terms that are the cross terms, which are d squared dp1 and dp2, right? Where then you also have the same term over here, right? So it's going to be symmetric. Technically, it is this, right? But if you assume that the gradient is differentiable, then remember that you can always swap your derivative orders. So under certain circumstances, you can then swap it to be this. Does anyone recognize what kind of matrix I've just written down, though? Right, this is the matrix of second derivatives, which has all the partial terms. This is equal to H, which is also known as the Hessian matrix, right? So the Jacobian of the gradient is the Hessian. And so another way that you'll find people write down Newton's method for optimization is that they say this is pi plus 1 equals pi minus the Hessian at pi inverse, and then the gradient, right? dc of pi dp. And so if you look in something like Wikipedia, they'll just say, oh, you calculate the Hessian, you invert it, you take the Jacobian, or you take the gradient, and then this is Newton's method for optimization. This shows you why this is actually exactly the same as what we were doing before, right? Just because it's exactly the same thing, it's just using this idea that the Jacobian of the gradient is the Hessian, and then simplifying the formula a little bit. But yeah, so this is where a whole lot of other techniques for local optimization come from. They say, well, calculating a Hessian matrix is really hard, right? Because you're calculating a second derivative. How can you calculate a second derivative with forward mode AD? Well, you can remember I mentioned you can have those double duals, or you could take the derivative of a program that calculates a derivative, and there you get second derivatives. But now you're thinking about, think about the growth and the number of partial terms you need to have. This thing gets big and difficult really quickly. So you generally don't want to try to calculate an entire Hessian. And so what people have done is they found techniques for iteratively approximating the inverse Hessian. So probably the most well-known is the BFGS technique. And then there's a low memory variant of that, LBFGS, which in these two methods are essentially, these and gradient descent-based methods are the standard techniques for local optimization. Some people do go directly to Newton's method for optimization. There are some good properties with it, but with stability and things like that, that you kind of lose when you go to these approximations. But generally, these Newton methods are considered to be, too expensive because the Hessian is fairly expensive to calculate. So you have methods which are either directly doing gradient descent, or you have methods which are approximating the Hessian and then using an approximate Hessian to be able to do the updates. So what's another way to think about local optimization? Well, here's a connection that you might not have seen before, and it's that let's look at this ODE, right? So let's say we have p prime equal to minus fraction dc dp. Right, so this is an ODE. Like the derivative of p is equal to the gradient of a cost function. So let's look what happens if you apply Euler's method to that, right? So let me write down what everything looks like in the syntax that we had before. So we were looking at things before like u prime equals f of u, right? And when we did this, we said that Euler's method was un plus 1 equals u sub n, right? So you take your current point and then you move forward by delta t by the derivative, right? So you take a derivative calculation and you say, I'm going to extend the line by the derivative by delta t, and this is Euler's method, right? Now let's look at what Euler's method is on this ODE. So you have p I plus 1 equals p sub I plus delta p fraction dc dp. Does this look familiar? Well, if you scroll up to here, you'll see that this is, if you extend this to now say that instead of just being, if you extend this to now say this is able to be some arbitrary parameter can be here, then, well, I mean, delta p is that arbitrary parameter, then this is gradient. Oh, I forgot this minus sign. So yeah, if you remember the minus sign in there, right, then so this is minus f, etc. That's where the minus comes from. You see that this is exactly gradient descent. So gradient descent is doing Euler's method on this ODE where you've chosen a delta p, and that delta p is the learning rate. Right, so this is another way to think about local optimization. You're actually trying to solve an ODE. This ODE is defined by, your ODE is given by, this is the slope. And what you want to do is you want to follow the slope to get to the bottom, right? This is a dynamical simulation. You want to just simulate the ball rolling to the bottom of the hill. And the easiest way to do the simulation of the ball rolling to the bottom of the hill is to use Euler's method. You pick a delta p and you do Euler's method, and that is gradient descent. And so there's a lot of different connections that you can start to pull from when you do this, right? So let's say, for example, you do a pi plus 1 equals p sub I minus, this is going to be at pi, right? So remember, implicit Euler is when you evaluate this function at un, but what happens if you do it at un plus 1? That's that's implicit Euler, right? So this was explicit Euler, this is implicit Euler, and so implicit Euler is going to be the method, which is by dc pi plus 1 dp. And so now you're going to have this nonlinear system. So you solve this nonlinear system via Newton's method. So in order to solve the nonlinear system via Newton's method, you have to calculate the Jacobian of your right-hand side, which this is the gradient of your cost function. And so the Jacobian of your right-hand side has the Hessian of your cost function. And so then you'll see that these Hessian-based optimization methods are equivalent to doing a ODE, an implicit ODE solver on this ODE defined by p prime equals minus the gradient of your cost function. So this is a whole nother viewpoint for understanding optimization, right? It's just you are trying to make a ball roll down the hill. Local optimization methods are just solving the ODE for how the ball rolls down the hill. They've chosen a discretization, and then you just run that discretization until you hit the bottom of the hill. There is a little bit more leeway in optimization, right? Because you don't actually care about solving this differential equation accurately, right? All that you're really looking for is at the very end, did I get to the bottom of the hill? And so a lot of different methods will put in extra approximations to the way that they do the dynamics here, because getting the dynamics exact isn't as important as getting to the bottom of the hill. So, but this is another way to understand, at least, that optimization itself is also highly connected to differential equations. So in a sense, I can say, solve a differential equation on P to get optimal parameters. But how do but what is this? What every single step of this differential equation, its right-hand side is the gradient of a cost function. So its right-hand side is you solve an ODE itself with parameters pi, probably dual numbers because you want to get the gradient, and so that's going to have a loop, and that's going to have a loop, and it's just loops all the way. It's loops in ordinary differential equations all the way down. Okay, so how does this connect back to neural networks then? Well, the key here is that neural networks, the neural network training process itself is a shooting method on a program, right? It is no different from taking this robot and saying, oh, I'm going to try these parameters, throw the dart. Now try new parameters, throw the dart, calculate a gradient. Try new parameters, throw a dart, calculate a gradient. Try new parameters, throw a dart, calculate the gradient. Right? This repeated process is exactly what you do in training a neural network. Right? So in a neural network, right, as we described earlier, you have neural network of x is equal to W3 sigma 3, right? So you do a nonlinearity around a matrix multiplication and a nonlinearity, right? You just keep on packing together nonlinearities and nonlinearities. Right, so we already went over this in this course for the physics informed neural network lecture. So I'm not going to describe what the neural network definition is again. But essentially, this is the mathematical form of a neural network, right? And so the way that you train a neural network is you take all your weight vectors and all your b's and everything, right? You say my p, my parameters is equal to this whole vector of wi's and bi's. And what do? You try a set of parameters, you calculate your loss function, you then change your parameters a little bit, and then you calculate your loss function again. This is exactly a shooting method. There's actually no difference. Um, so you know, so this is where the things start to connect, right? So doing parameter estimation by doing gradient descent and shooting methods on simulators is actually the same process as what people call training on a neural network. It's all this process of fix parameters, run your simulator, calculate gradients of your simulator, change your parameters, start this process over again. So both of these things are heavily related. Let's see. I'll I'll move that to the next part. So, okay, so how do you actually compute gradients in this sense? It turns out that calculating gradients of a simulator, right, be it a neural network or a neural network inside of a cost function, or be it a ODE simulation inside of a cost function, or some other simulator of a high performance simulator of a high energy physics calculation or anything, all of these processes all come down to just calculating gradients of the simulation process or the model. And why is that the case? So I'm only going to do the derivation on a specific example of a cost function, but it should be fairly clear why this extends. So let's look at the cost function. Sum of I to the n is equal to vert f of xi p minus yi. Right. So what I'm writing down here is I'm saying, we take parameters p and we solve the differential equation. And what we want is we want some value. We want the xi value out of it. So maybe it's like, the ith time point of variable one, right? So whatever this xi ends up being, right? So we have data to match this, right? So think about like the Lockville-Dare example. So let's say we have a whole time series of the wolves over time, right? So what I'm saying here is, for each of the i's, so each of the points where we have a data point for how many wolves there should be, we run the simulator once, and then we check the output at that point, and it says the number of wolves in the simulation at t equals 5 is equal to 2.2. My data yi says that it should be 2.5, and so this is the difference, right? And do this for every data point. You run the simulator, get the output. I mean, in practice, what you actually do is you run the simulator once, and then you check the output at all points. But it's easier to write this down in this fashion, right? So you run the simulator, you check how close you are to data, you sum all of those differences, and this is the sum squared difference loss function. This is quite a standard one. Right? So you're taking the Euclidean distance from every single point. If you're thinking about this with the robot, right, you choose parameters, and then you throw the dart. This difference right here is just say, if you've thrown n different darts at different dartboards, what we do is we sum up the differences from being a bullseye. And what we're going to do is we're then trying to find out how to make them all be a bullseye, right? So this is a little bit more generalized. Okay, so this is the thing that we want to optimize, right? We want to find the parameters p such that everything that we get out of the simulator matches the data that we have. And so we do dc dp, right? We want to calculate the gradient because we're going to do gradient descent. And if we calculate the gradient of this function, what we get is by the chain rule, 2f of, well, this is going to be a absolute value, f of xi p minus yi, right? So we do the gradient of the outside because this is the, if we're just to think about this as a scalar, this is just a squared, and so then if we're to differentiate this, we have 2 times the middle times the derivative of the middle, right? And what's the derivative of the middle? Well, this part is constant, right? Which means by chain rule, there's a derivative of this term that comes out. So df of xi dp. And what does this mean? This means that what we need to calculate in order to get the gradient of the cost function is we need to calculate what the gradient or what the derivative of what came out of our simulator at a given point, what its derivative is with respect to p, right? So if we think back to that example, right, when you run the simulator, it outputs something like at time t equals 3, I predict that the number of wolves that you will have is this, right? What we want to find out is what is the derivative of that prediction with respect to the input parameters, the parameters that you put into your simulator. If you have those gradients, those are the only gradients you need in order to write down the gradient of the cost function, and then you can run gradient descent or Newton's method or any of these things to be able to calculate what your what the next parameter should be. So this is what I mean, right? So normally in your cost functions, the derivative of the cost function is fairly simple, except for the fact that it asks for the gradient of the derivative of the output of your simulator with respect to the parameters that you put into the simulator. That's always a term that will show up. And why does it always show up? Because that's a direct consequence of the chain rule. Because if you put f in any of these nonlinear functions, and f is in your simulator is a function in your parameters, by the chain rule, this term will show up somewhere. And so the problem of doing parameter estimation, like the computational part of it, is always how do I calculate the derivative of my simulator with respect to input parameters, right? Now think about this as being the neural network, right? So if your model is just the neural network, the same exact process applies. And so what all you need to do is you need to calculate the gradient of a neural network with respect to parameters, and that will tell you how to get the gradient of your cost function, and that tells you how to then do gradient descent, right? And so this is essentially what PyTorch, TensorFlow, Flux. That's the process that these frameworks often automatically do for you, right? They tell you how to automatically get the derivative of neural networks. So then they piece this into these cost functions, and this is how they end up doing gradient descent or ADAM or any of these training techniques. But what we're doing now is we want to say this could be any possible simulator, and we want to differentiate through any simulation code. What would that look like? How do we get these derivatives? And this is actually also the key part to your homework, right? So how would you do forward mode automatic differentiation to do gradients, right? Why forward mode? Well, it's because we've already explained it. We already know how to do it. So let's just do it, right? Um, so what you would do is you'd say, let me create a dual number which has a primal part, right? And I have a partial dimension for each of the things I want to calculate the derivative of. If I want to calculate n derivatives, and because I need to calculate n different columns here, so I'm going to put n different partials in here, and this will give you the this will give you the gradient, right? So note that what am I going to be differentiating my singularity with respect to? Well, I'm differentiating it with respect to parameters, right? So while all of our discussion before was about, you make the state of your ODE be dual numbers, and that's how you get the Jacobian. Well, here what we want to do is we want to make the input parameters into our simulator be dual numbers, right? With directions being the E1 through En, the elementary directions. If we put these dual number parameters into our simulator, then what will come out of our simulation is every single prediction, right, will be the primal part, because it always keeps the primal part the same, right? So the simulator will spit out predictions, but also you'll get the derivative of that specific prediction of the simulator with respect to input parameter 1 through input parameter k, right? So you can use dual numbers. You just have to make sure that now you make all of your parameters be dual numbers. And what you're looking for the derivative of is the output of your simulator. Your simulator will now output dual numbers, and the partial parts of those are the derivatives of those pieces, of those specific what it'll output is the derivative of those specific predictions with respect to given parameters. And then from that, you can piece it back into this equation we have here, be able to, you pull out all these partials, and you put them into the gradient of your cost function, right? You put it into this chain rule term, and that will give you, that gives you dCdP as some function of these extra terms that come out of the dual number, right? So this is precisely what you're going to be doing in your homework, right? So in your homework, you are doing a different way to do forward mode AD of a ordinary differential equation. They're actually equivalent, but But yeah, but what you'll do is you'll define this way to be able to get the derivatives of the ODE solution with respect to parameters. And once you have all those different derivatives by solving these extended ODEs, you put them into the derivative of your cost. You put them into this function. You calculate the derivative of your cost function. Once you know how to calculate gradients to your cost function, then you can do gradient descent. And you iteratively do this process of calculating new gradients and changing parameters around. Right? So this is the whole process. But can we do better? Right? So the difficulty here is that we've now actually increased the size of our simulation gigantically. We'll describe this in well, right. So if we're thinking about our ODE simulator, right, like what we had before, we had something like, think about Lock-Volterra, right? Lock-Volterra is something where, let's say we had 10 outputs that we wanted to calculate. We would have a function which goes from P to, ODE output predictions. P goes to ODE output predictions, and we might have, 4 parameters going to give us, like 20 predictions, right? So this function can be feasible, right? Like if we have 20 predictions in our time series, this function f is a function which takes in a vector of 4 parameters, spits out a vector of 20 things, and that is a computation that can be difficult, but it's not exceedingly difficult, right? But now we're changing our input to be something that is actually a it is a number type which is now going to have k times as much per parameter, right? So each parameter now grows from being a 64-bit number to being something that is 64 plus 64 plus 64 plus 64, right? Because it has all these different partial terms. The total size of this vector, right, since we need to take the derivative with respect to each parameter k to calculate each of the terms of the gradient, right, that means that the size of the numbers that we're using now is going to be k plus 1 dimensional, right? So if we have k parameters, then every single number is k plus 1 dimensional. So if we have 4 parameters, then our input space is, now we have 4 parameters times each dual number has 5 numbers, and so our input space grows from 4 to 20, right? I'm not saying so right. So now our input to the simulator is, we have a P1, we have P1, P2, P3, P1, P2, P3, P4, right? If we have 4 parameters, like in that homework problem, the input into the simulator is now going to be like P1, 0, like what the actual parameter is, plus E1 epsilon 1, right? So we put this E1 in there for to say, oh, take the derivative of this epsilon term, right? And we have 4 epsilon terms. So if you actually look at this whole matrix, our input into the simulator is now 20 numbers. And so what we actually have to do is we have to grow the calculation to do so if we have k parameters, the input size grows to k plus 1, or if I'm thinking about it correctly, it should be k plus 1 times k. Right, so it's actually going to grow squared, right? Because as you get more parameters, you're going to be making there be more columns here and more rows, where the number of columns, if you think about this as a matrix of numbers, the number of columns here is k plus 1, and the number of rows is the number of parameters. So when you do this process, if you could have large numbers of parameters, your simulator, which you thought of as being, oh, it's just 10 parameters, now to calculate the gradient of it with forward mode AD, it is now effectively a 110 parameter simulation. If you think, oh, I have something with a small number of parameters, like a pretty large number of parameters, 10,000 parameters, if you want to calculate the gradient of that, the gradient is effectively going to be a simulation with millions, parameters, or whatever 10 squared is going to be, or 10,000 squared. The 10,000 squared is equal to, yeah, 100 million. So if you have, so in the simulation, which with 10,000 parameters, calculating the gradient of it is about has the same computational cost as a simulation with 100 million parameters because of the squaring property. And so forward mode automatic differentiation is not really an effective way to do this if you have a very large set of parameters. So can you do better, right? Like, forward mode AD is very good. It's very efficient. It is an accurate method if you have low numbers of parameters. But is there a way to make it so that way the number of things that we're taking derivatives of doesn't have to grow quadratically with our input size? So this is where the adjoint technique and reverse mode accumulation comes. So this goes under very many different names because it's been used in very many different fields. And so a lot of what this might actually be, this portion, is really just helping you understand how something that you might have learned in a different context can be reinterpreted in this new context. So this technique right here is known as the adjoint technique, backpropagation, reverse mode automatic differentiation. These are all, in some sense, the same technique, right? So the function that we want to look at to really define this technique is f of x of t, y of t, right? So let's say we want to take derivatives with respect to t of this function, right? So the inputs to this function f are x and y, but to calculate x and y, you need to calculate them as a function of t, right? So let's say we're just to do two layers of functions like this, and let's analyze how we can effectively calculate the derivative of f with respect to t, maybe in a way that's better than the naive way of pushing down these of doing a derivative with respect to t directly on f. So recall by the chain rule that what you would do is df dt is you would do you take the derivative of the first part and then you plus the derivative of the second part, right? So this is going to be the total derivative with respect to t is going to be df dx, and then the derivative you have to do the chain rule, right? So then the next term is going to be dx dt because x is dependent on t, and then you do your other derivative, right? So this is going to be sorry, this should all be partials, the partial f partial x and dxct, and then this other term is going to be partial f partial y dy dt, right? So this is just the multi-dimensional chain rule applied to the function f. So you can visualize this as a computation graph, right? So if you know the value t, you use that to compute the values x and y, and then you use x and y to compute f. So this is the computation graph way of thinking about how you can stack together these programs. So this is basically a program with multiple steps, right? You take in t, you calculate x, you calculate y, then you calculate f, and that's your output. So when you think about taking derivatives of programs, you can also think about them as, they're just layering functions of functions of functions, which you can interpret as a computational graph. So now assume that you've already calculated f of t. If this has been done, then you've already had to calculate x and y, right? Because of this dependency chain. And so given f, you can now calculate df dx and df dy because you've already had to do this calculation. So if you did forward mode, you would have pushed forward a dual number here, pushed forward a dual number here, and so you'd have the gradient of this. But then because you'd have to push forward these dual numbers, you'd also have the gradient in this term. And the gradient of t with respect to t is trivial, right? And so this is the way of thinking about pushing it all forward, right? But now let's try to see if there's another way to calculate gradients, right? Instead of pushing gradients forward, is there another mode that we can do in here? And so to see how to get there, let's add another layer to the computation, Right. So now we're thinking about this as f of x of v of t, w of t, y of v of t, w of t. All right, so now we're just layering the computation once more. What would the total derivative look like in this case? Well, this would be df dt equals df dx, or partial f partial x dx dt, right? So this comes from the chain rule, and then this other term comes from the chain rule as well, right? So this is just once again a multi-dimensional chain rule, and what we should notice is that this is exactly the same equation that you got when you only had one layer, right? So if we want to look at when we first write out the chain rule for df dt, if this is a function of x and y, it doesn't matter what happened underneath the hood. The last step in this calculation is always going to be the same. Okay? But now, if we have more details in here, I need to expand out what is dx dt, and I need to expand out what is dy dt. Now let me expand those parts out. Right, so dx dt is equal to the partial of x with respect to v, and the derivative of v with respect to t, right? And in this other term, it's the partial of x with respect to w. This is just once again the multidimensional chain rule, right? And you have this exact same relationship for the y term as well. So the derivative of y with respect to t is equal to the partial of y with respect to v and the partial of y with respect to w, right? So this is the interesting thing here, right? That this last part of the calculation, it doesn't matter what else happened under the hood. This last part is the same. It's just when you change the function for f, you then have another layer in here that you then have to push back through, right? So this is where we start to look at reverse mode accumulation, right? So this is the idea. Noticing that when you have this function, this is the chain rule. When you have this function, this is the chain rule, where we then just have to do the chain rule here, then the chain rule here, the chain rule here. And you can see that if you have multiple steps going down, like if v was a function of et cetera, you could keep on doing this, but every step of the way down only needs the stuff behind it in some sense in the computational graph. So I'm going to walk through examples. If that is too quick for now, we're going to be doing a lot of examples. So if we had more layers, we can calculate the sensitivity. So I'm using the term sensitivity as something that is analogous to the derivative. So if we had the derivative with respect to the last layer, then we can start to try to use this to find out what these terms are. Well, okay. So let's take a step back here, right? So if we want to calculate this term, right? If we want to calculate df dt, well, getting the partial of f with respect to x is something that we can just use the f equation, right? We can use what we've already computed. One step back here. So let's say we have done a computation to compute f, but we've stored all of the intermediate parts of it, right? So we've taken in t, we've calculated x, we've calculated y, we calculate f, right? Now let's say I want to calculate df dt. What this formula tells me is that I can take what I've already computed as the point x, and then I can take the partial derivative of just this f function, so just the outer function, just the last function, and the partial derivative of this last function at this point with respect to the first input at the point of this x that I've x of t, that will give me this df dx, right? And do the same to get df dy. And so if I just have what the output of the forward computation for x of t is, then I can use that to get these terms in the derivative. And now what this second part is telling me is that if I have more layers of the computation, I can calculate these two terms independently of what's going on down here. And then if I have more stacks, I can calculate these gradients independently of exactly how x of t, exactly independently of how v and w are working, and I can start iteratively going down this. But if you think about it, the information that we're using is we're calculating the partials with respect to f, and then the partials with respect to x, the partials with respect to y, and we're able to calculate the partials in the reverse order of the forward mode. So let's do this on an example that is a logistic regression, right? So a logistic regression is, you can piece it together as these different pieces, right? Where you say, I have a value x that comes in, right? And the way that I'm going to evaluate my loss function is I'm going to do a linear transform on x. So I'm going to say z equals wx plus b, where this can be, for now I'm going to make this scalar and a scalar, but these could be vectors. So I do a linear transform of my input, and then I do a sigmoid on that, and then I check what the square distance is of my prediction from my model is from my data. Oh, and then let me add in a regularization term. So I'm going to say, I want this, I want my W to be as small as possible. So in my true loss function, I'm going to take so in my true loss function, what I'm going to do is I'm going to make my loss function be the distance of my prediction from my data point t, and I'm going to add in this term, which is the square of my weight, because then maybe that will decrease the weight into something, right? What I want to do here is I want to find the derivative of the loss function with respect to the weights w and b, right? You can see that this is kind of like a simplified neural network example. So let me go through that again. We basically have a mathematical form of a computer program, where what this computer program does is it takes your input, it multiplies it by w, it adds b, it puts it into the sigmoid function, and then checks the square distance of the sigmoid function from the of that output from the data point that you want to fit, and then it calculates this loss function, which is, you take the w that you have, you square the w that you have, and you add that extra term to the distance that you had, and this is the scalar value it outputs, right? So this is what it calls the regularized loss, and you stick x in, you get a regularized loss out, and we want to find out what the w and b parameters would be to make it so that way this loss function is minimized. Okay, so we represent this program then as this computational graph, right? Where x comes in, b is a parameter, w is a parameter that comes in. We use these to calculate z. We use z to calculate y. We use y to calculate our loss. We then use our data point to calculate what the loss is with respect to our predicted y. We also use w to calculate our regularization term, and we stick these two together to give our regularized loss. Right, so this is the flow of the data through our program. So now let's calculate the derivatives with respect to each of these quantities in the reverse order. So our program is x comes in and the regularized loss comes out, right? So we can think about our program as f of x equals the regularized loss. So now let's do this process that we had before, just doing multidimensional chain rule, and see how this process would give us derivatives that we can calculate. So our program is f of x equals mathcal this regularized loss, right? And what we want to do now is we want to be able to find out how to calculate the derivative of f with respect to these parameters b and w, because these are the things that we'll want. And these would be the gradient of our cost function based off the regularized loss, right? So how do we calculate gradients of these things using this reverse mode accumulation idea? So what is first of all, at the first layer, you have to figure out what is d math down loss reg df. Well, this is equal to 1. This is trivial, right? So what is the derivative of this function with respect to its output? It is equal to 1. This is a weird detail. I'll come back to why this shows up in here, right? And so what I'm going to do to make this notation a little bit easier is I'm going to use overline mathcal lreg to represent this derivative, because we're going to have a lot of derivative terms around. And so whenever I've written down a formula to calculate such a derivative, I'm going to say that this overline version is just the derivative that we know how to calculate, right? So now let's do this chain rule idea, right? Let's do this reverse chain rule idea. So the so if you write this down, we have that dr let's see, the derivative with respect to the derivative of r with respect to Lreg is going to be equal to df d Lreg, and then d Lreg dr. Right. So sorry, there's an issue here in the notes. Right. So the RDL reg is just df dl reg dl dr. Right. Sorry, this is the wrong term. It is df dr. Right. So whenever I put an overline, it is the derivative of that thing. So this is overline L reg is equal to df dl reg. Right. So this term overline r is df dr, and if we actually write down what this is using the chain rule, what we have is df dl reg dl reg dr, right? It turns out, what is the derivative here? Well, the only thing that you need to know in order to calculate this derivative is you need to know this last function, right? So this last function is just that, well, what is the derivative of f? F is Lreg, right? So what is the derivative of this function with respect to r? Right, so it is the derivative of this with respect to r is just lambda. And then what is this term right here? Well, this is the term that we've already computed. It is Lreg bar, which is equal to 1. Right, so you have Lreg bar, which is equal to 1, right? So this is a weird detail, kind of gloss over for now. I'm going to get back to it. And then this other term right here, this term is lambda. Right? Why is this lambda? Well, because the output of this equation, its derivative with respect to r is lambda. Okay. And this is where you can start to try to see where the pattern is. Right, so how does this relate back to what I was showing you here before? Right. Well, what I'm showing you is that the derivative of the output with respect to t, right, is only due to partial derivatives of the last function and things further down. So what I'm looking at right here, right, the derivative of f with respect to r is there's a term which is the partial due to the last function, and a term which due to other derivative terms, which in this case happens to be something that we already know the derivative of, right? Because we know the derivative of f with respect to Lreg. It's 1 because f is a function that outputs Lreg. Okay, so bear with me a little bit. I think that you need to do a few. It's like the Ramanujan writing down numbers thing, right? Just you got to do enough of these computations, and after you do enough of these computations, you start to see the pattern. So let's do the next one, right? So overline L, mathcal L, right? This is the thing that I'm saying is df d mathcal L, right? This derivative is by the chain rule. It's going to be df d mathcal L reg fraction d mathcal L reg mathcal L or dl, right? So what is dl reg dl? Well, it's equal to 1. Right, so this is going to be equal to df dl reg, which is just L bar L reg times 1, right? So I'm just going to omit the 1. So let's look at what we've done so far, right? So we can do a forward pass, and now at this point right here, we can say, well, what is What's the derivative of the output of this function with respect to the output of this function? It's 1. Okay. Now, what is the derivative of L with respect to the output of this function? Well, by the chain rule, it is the derivative of the output of the function with respect to itself. Um, by the chain rule, it's the derivative of the output of the function with respect to itself times the partial derivative of the last function call that was done. And the partial derivative of the last function call that was done with respect to r is lambda. So we do lambda times the derivative of the output. And then the other partial derivative is 1, right? So this gives us what the derivative of the output of this function is with respect to L, and what the derivative of the output of the function is with respect to R. Think about this again, right? I've written it down formally, but think about it just in lazy terms, right? L reg is equal to L plus lambda R, and basically what we're saying, and L reg is the output of the program. Basically what we're saying is, what is the derivative of L reg with respect to L? Well, it's 1, right? It's 1 written in a different way. And what is the derivative of L reg with respect to R? It is lambda. Lambda written in this other way, where I'm keeping around this df/dl reg term, which is just 1, right? We'll see why I'm keeping that term around. But now let's do one layer back. Okay, so we know we've used the derivative here to calculate the derivative of this with the output of the derivative of the output of the function with respect to this value, and the derivative of the output of the function with respect to this value. So now let's go one more layer back. Let's go down to y. What is the derivative of the output of the program with respect to the value of y that we get in the program? Right, so the derivative of the output of the program with respect to the value y is this thing that we're going to call overline y, which is going to be equal to, well, it is going to be the derivative of the of f with respect to math cal L, and then it's going to be by the chain rule, it's going to have the d math cal L dy. Right. So why am I writing it like this? Well, the reason why, so let's see that this is true, right? Because the way to think about the chain rules is always if you cancel these terms, then you have df dy, right? So this looks like a really odd way of writing the output of the program with respect to y, right? The derivative of the output with respect to the program the derivative of the output of the program with respect to y is equal to the derivative of this thing that shows up in the middle of the derivative of the output of the program with respect to this thing that shows up in the middle of the program, multiplied by the derivative of this one computational step in the program with respect to y. Why did I write the derivative in this form, right? Like this is the chain rule, so it's correct. But why would I write it in terms of something that is in the middle of the program? Well, the reason is because df/dl is this quantity L bar that we already know how to calculate, right? So we simplify this to here. And what is dl dy? Well, we can take a look at this one step of the program, right? This one step of the program is a function that takes in y and it spits out L. We just differentiate it, right? So what is the derivative here? This is going to be, right, so I chose everything so that way it's easy, right? So the 2 comes down, you multiply by 2, the constants cancel out. And so the derivative of this one line of the program is equal to y minus t. So df dy equals whatever the derivative of this term was times the partial derivative of the program that calculated L from y. And now we start to see the pattern, right? This is exactly the pattern. The derivative of L the derivative of the output of the function with respect to L is equal to the derivative of the thing that came after it, or the derivative of the output with respect to the thing that came after it, multiplied by the partial derivative of how to do this next calculation. The derivative of the output of the program with respect to y is equal to the derivative of the outputs that are calculated from y multiplied by the partial derivative of the things that are calculated from y, right? And so notice that the derivatives are always written in terms of the things that you calculate from one. And so this is why it's starting to go backwards, right? If you know L bar reg, then you can write down L bar in terms of L bar reg, and you can write down Y bar in terms of Y bar reg, and so you can reverse accumulate these derivative calculations. Right, so all of these calculations, what they have is they have this derivative term from the thing after multiplied by the partial derivative of how that output was calculated. If you look back at the chain rule, that's exactly what we were saying above, right? That there's always a partial derivative term, right? So there's this term of ignore everything below me. This is just a function of x and y. Calculate the partial with respect of f with respect to x, right? So calculate your partial derivative, and then there's some other derivative term here, and then this is the other thing we have to calculate. So here, in thinking about it like that, there's a partial derivative term, which we just look at that one specific function. That's how we get that partial derivative. The other term just happens to be a derivative term that shows up in the later part of the program. So we've already calculated it. And so we put that constant here, then we put in this partial derivative, and this now tells me how to do df dy, y bar. And now let's look at this going back once more, right? So df dz is equal to, well, this is something we're going to call overline z. This is equal to df dy, fraction dy, df dy, and then dy dz, right? So this is the chain rule to be able to write this thing down. Now, why did we write it like this? Well, df dy is equal to y bar, where we know how to calculate y bar. Y bar is L bar times this. L bar times this is equal to, well, L bar, we know this, right? We know all this information here, right? So y bar is now something that we can compute. And then this dy dz, we go back to our equation, which says, well, we calculated y as sigmoid of z, and so dy dz is just the sigmoid, the derivative of the sigmoid with respect to z, right? And then you could do the next step, right? The next step is actually going to have another detail here, right? So this is where we start to say df dw, right? Well, remember back in this case that if you had two inputs, or if you had two inputs, you need to start summing things together, right? When we've been going back, we've only been having one of these out, or when you have two outputs, you have to be summing things together. Here, we're going to be doing that again, right? So W shows up in two computations, and so it's going to have two things, two things summed together for what its reverse mode accumulation rule is. So how do we write that down? Well, we're going to have df dz, dz dw, and then we also need to say this term of df dr dr dw, right? Because what is the derivative of the output of the program with respect to w? Well, there are two terms that it affects. It affects z and it affects r. So we can write down the derivative of the output in terms of the derivatives, how the output is changing with respect to z and how the output is changing with respect to r, right? This is another way to think about it. We have, we could say the derivative of the output with respect to w is built on the derivative of this one arrow and the accumulated derivative of z all the way to the end, right? And it also, the derivative of the output is also dependent on this one arrow and something due to the derivative to the end, right? So that's precisely what we're writing down here, right? So this df dz is the derivative of the output with respect to all these arrows combined, and zdw is just this one arrow term, and that gives me this from w to the end. Df dr, dr dw is just the arrow to the end, right? So you can. This is another way to think about this computation, right? And now, if you think about it like that, this df dz term is just z bar. And then we have dz dw, where dz dw is just equal to x plus df dr da, da, da. This is going to be r bar over line r. So r bar times the derivative of r with respect to w, which is just going to be w, right? But maybe it helps to think about it in this other way as well, right? Like I'm going to give you like 10 ways to think about this, and whichever one works for you, that's great. So the other way to think about this is, you know, the way to calculate the derivative of y, or the derivative of the output with respect to y, is that if we look back at that equation, the derivative of the output with respect to y is equal to the derivative, this arrow right here, how much the output changes with respect to what's going on here, and the output of what changes with respect to what's going on here, right? When we put those two arrows together, that's how you get the full derivative. And by the chain rule tells you that the way that you put together arrows is you multiply. Now the derivative of the output with respect to z is going to be the derivative of how change happens with respect to this arrow, and the multiply for and how these two arrows combine give the output. But how these two arrows combine to give the output is the derivative of the output with respect to y. And so it shows up right here. And so then we only what we do is we write down, oh, the derivative of the output with respect to z is what is the derivative of this one arrow multiplied by the derivative of all the arrows that come after it, right? So this is another way to kind of visualize what's going on. And that also shows you why it's reverse mode accumulating, right? Because we're collectively building a bigger and bigger arrow going backwards until we're finally at this point w where we say, well, the derivative of f with respect to w is just whatever the derivative of this whole thing is, whatever that is, and the derivative and how much things change due to this arrow. But this whole thing is just z bar, right? Because it is the derivative of this arrow multiplied by the derivative of this whole thing, which is the derivative of this arrow multiplied by the derivative of this whole thing, right? And so each time we're just putting one more arrow as we go backwards until we can write down df dw as just, oh, you've already calculated that times x, and oh, you've already calculated that times w, right? And this is how we get to reverse mode accumulation, right? Now we're saying that the way that we calculate the derivative with respect to this input parameter is you first calculate the derivative of the output with respect to itself, you get a 1. Then you calculate the derivative of the output with respect to the last function, like the last line of the function. You take the derivative of that to be able to get its own partial derivative, and now you have L bar and R bar, that tell you how these last arrows work. And now the next one back, the next derivative back, how the output changes with respect to y, is just going to be how the output changes with respect to L multiplied by how L changes with respect to y. Well, you've already calculated this term, so you just multiply that to the derivative of just one part of your function right here. Just multiply that to the derivative of just one term of your function, right? And you just keep on repeating that process going backwards. Or now that you've calculated the derivative of these two things together, well, the derivative of z is just the derivative of one step of your program multiplied by the derivative of all steps that come after it, which is y bar, right? And you then can keep on pushing this back and back and back. If that didn't make sense, then you might want to go through that explanation multiple times. You might want to start doing some of this by hand. This is a pretty important thing to understand, and I think that you need to do the calculation how to understand it. But essentially, the way to do this, right? You can basically just look at the graph, and if you do this with the chain rule enough times, you find these rules, right? So these rules they come from doing the computation many times. And the way to think about these rules are, let me kind of get two versions of this open. Actually, I think for the online format, sorry, I think I have to do a bunch of scrolling here. So, oh, actually, I have these equations right now here, right? So dw has two terms, right? Which is essentially whenever you have two output arrows, then you're going to have a summation of the two of the derivative with respect to those two outputs. So that's one rule. The other rule is that each arrow has a derivative term of the end times the partial of the current term, right? So so what is, so if I have an arrow here, then that means I have, I have two arrows coming out of W. That means I have two derivative terms. What are the two derivative terms? Well, the two derivative terms are going to be the partial derivative of how you calculate Z with respect to W multiplied by Z bar, and the partial derivative of how you calculate R with respect to W multiplied by R bar, right? You see that's the equation that you get. You can kind of just start to read off the graph, right? So what is the derivative of Z with respect to the output of the equation? It is going to be Y bar multiplied by the partial derivative of Y of how Y is calculated, its derivative with respect to Z, right? And so that's the rule, right? You take the partial derivative of, you put the bar on the thing that comes after it, and then you use the partial derivative of how that term gets calculated with respect to the input, and then you just add together you add together all the different branches that can come from these different output arrows. And what's the third rule? Well, now you recurse backwards, right? Because the derivative of Z of the output with respect to Z as the Y bar is Y bar multiplied by this partial derivative. We can calculate this partial derivative easily, but the hard part to get is Y bar. But Y bar is given as L bar multiplied by the partial derivative of L with respect to Y. And so you just need to calculate L bar, which you get L bar from the L reg bar, etc. Right? So you first get the first bar, you get the derivative of the output with respect to L reg, and then you use that to get the derivative of the output with respect to L, and the derivative of the output with respect to R. Use those to get the derivative of the output with respect to Y. Use that to get the derivative of the output with respect to Z. Then you use that to get the derivative of the output with respect to W, and then derivative of the output with respect to B, right? And that's why it's reverse mode accumulation. You're walking through this graph kind of in the reverse order because you know that the derivative of this one arrow right here, or the derivative of Z to the final output is, Y bar times the derivative of Y with respect to Z. And if you do this out enough times, and then you see that these are your three rules for how you can calculate the derivatives in a way that is reverse accumulating the information. And so essentially, you do a forward accumulation, and then you do a back, and you push forwards all the values, and then you fall backwards with all of the gradient calculation. So why do you need that push forward? Well, think about this. You have terms like you need Y inside of here, right? Where does Y come from? You need it from the forward path. So so the way that you do this way of calculating the gradients is, let's say you want to calculate the gradient for some input x, and you want to calculate the gradient of f of x with respect to w and b being these parameters of the program, right? What you do is you put x, w, b into your program. You calculate z, you calculate y, you calculate l, calculate r, you calculate L reg. Then you say d of the output with respect to L reg is 1. And now you say, well, then you get the derivative of the output. Then you calculate R bar. R bar is the derivative of the output with respect to R. It is L reg bar multiplied by this one partial derivative. So you just take the partial derivative of this function, you multiply it by L reg bar. That gives you R bar. You take the partial derivative of this function, you multiply, then you multiply it by L reg bar, and that gives you L bar. Sorry, you're doing partial derivatives of this function. Sorry. So then you move back one step, right? And you say, okay, what is the derivative of the output with respect to y? You take the partial derivative of this function, and you use L bar. You take the partial derivative, and then what is the derivative of the output with respect to z? You do the partial derivative of this function with respect to the, and then you use y bar in that equation. So when you do these partial derivatives, there are these values y and t that show up. Well, what are these values y and t? These are the values that you calculated in the forward pass of the program, right? So you do have to do one forward pass to be able to say what's z, what's y, what's l, what's r, what's L reg, and then in the reverse pass, you will have saved that information of what y is in the forward pass, And when you get to the derivative of y bar, you see that, oh, I need to go grab that information off of the heap, because the derivative of the output with respect to y bar needs to know what the value of y was forward pass of that program. So that's what this is trying to show here, right? That you're pushing forward information in your program, right? You use a w, x, and, z, and b to calculate b, or to calculate z, and then you use z to calculate y. So you push forward the information, and then you push backwards the information about the derivative. And so this right here is backpropagation or reverse mode AD, kind of in this general sense, thinking about it as computation graphs, right? So you can either think about it as we have a program which is composing functions, right? It's a function call of a function call of a function call of a function call, or it might be easier to write it down as, I have a step that calculates z, then I have a step that calculates y, then I have a step that calculates L, then a step that calculates R, and that calculates my output, right? These two ideas are the same exact thing, right? Because you can say that LReg is a function of x. You just have to, say it's the composition of function of function of function of function. So these two ideas are equivalent. So this is really the way of thinking about what is backpropagation for an arbitrary program where the program is just some composition of steps. So what is backpropagation of a neural network? Like, how would we think about what neural network backpropagation is in this generalized sense, right? Well, we just write down a neural network. A neural network is you do a matrix multiplication, add a vector, right? So this is the first thing that you do is you do that first input layer of a, you do the linear change to the input. That is the first step of the neural network. Then you do some nonlinear function, right? And then what we do here is we're saying, well, we calculate the output as the squared error from the data, right? So this is just like a one-layer neural network in a sense, where we just do a matrix multiplication, we do a nonlinearity, and then we're checking the output. Well, then we do another matrix multiplication, we add another vector, right? So this is a neural network where we have matrix multiplication, nonlinearity, matrix multiplication. That one layer was all right. Let's check against the data, right? So it's a very small neural network, but you can kind of see how to go to a deep neural network from doing this. You can just write down the computation graph, right? So the output is calculated as, well, you have your two data points. You have your two data points, but your output's also a function of y1 and y2, where y1 and y2 come from this layer of the neural network, where these come from this layers, or these come from these layers, and you have all these parameters feeding in at different parts of the computation. You can then run that same exact process, right? I don't want to write everything out by hand again, because now we know the rules, right? The rules are the derivative of the output with respect to the output is 1, so L bar equals 1. And now the way that we calculate the derivative of the output with respect to yi is it's just going to be L bar multiplied by the partial derivative of L with respect to y1. The partial derivative of L with respect to y1 is the 2 comes down. This is y minus, yi minus ti, right? And so that's where you get this term. And so the derivative of the output with respect to wij2, well, it is just going to be the same rule, right? So it's going to be the yi bar multiplied by the partial derivative of yi with respect to w, which is, the partial derivative of this with respect to w is just this based on this term h, right? So you just have yi bar h. Right, so now we're just using the rules, and the rules are telling us how to accumulate the derivative in a very easy way. And what is the derivative of b2 of y? What is the derivative of the output with respect to parameter b2? Well, it's just going to be yi bar multiplied by the partial derivative of how you calculate y1 with respect to b1, b12, which is going to be, well, the derivative of this with respect to b12 is just 1, right? So that term cancels out, and so you just have yi bar. Keep doing the rules, right? So now h1, what is the derivative of the output with respect to h1? Well, there's two terms, right? Because there's two arrows that come out of H1. And so therefore, what I need to have is I need to have y1 bar, and I need to have y2 bar. And those are going to be multiplied by the derivative of y1 with respect to h1 and the derivative of y2 with respect to h1, right? And so that's exactly this, right? So you have y1 bar multiplied by the derivative of y1 with respect to h1. The derivative of y1 with respect to h1 is just the weight matrix, the second weight matrix, right? So you use the values from the second weight matrix, and then you do the same process for the other term, right? So you just sum all the different outputs, right? You sum because full output arrows means you sum because that's how the multidimensional chain rule turned out, right? You move back. You can keep on walking through this and you see how to do this. And now the interesting thing here is that if you bring this back, right? So you say this was the whole calculation done where I'm looking at each of the scalar computations. You don't want to write everything down as scalars. You want to write things back as linear algebra, right? So what is this term as linear algebra? What is this term as linear algebra? If you do that, what you see is you can write down the vector form of this process, right? So I have a loss function, which is a scalar, but y is a vector, and it comes from a matrix and a vector, which comes from a vector, which comes from a vector, which comes from a matrix and a vector, right? So this is the computation graph written out as scalars, and we can calculate what the derivative of the output with respect to every single scalar is by using that process that we defined before. But if we actually look at what we got out of this, we can reinterpret it back into this easier form, this form as, oh, we have vectors and matrices, right? And so we can instead write our neural network as Z is computed as a matrix multiplication plus a vector. We do a element-wise nonlinear operation. We do a matrix vector multiplication, and now we do a loss function, which is the sum of squared errors, right? So it's exactly the same process as this. This looks hard to read because it's all in scalars. This is how you like to read it, right? But it's the same exact function, right? So if we now reinterpret the derivatives that we've calculated scalar-wise back into the vector form, what you get is this, right? Where you have L1 bar equals this, Y1 bar equals exactly the same thing, just as a vector notation. W2 bar equals Y1 bar times H transpose. So this is interesting, right? Because before we had Y1 bar H, now we see that to get these terms to write it down as a vector, what we have to do is we have to transpose this term right here. How do we know that's correct? Well, because we can if you take this vector equation and you write it out in terms of all the i's, and then you write down this this vector equation in terms of all the i's, you'll see that in order the correct vector notation for this to work out is you have to have a transpose on this term. This term was easy, right? This term's trivial. What about this term? Well, this term written back out as in its vector form, this is actually just the weight matrix transpose times y bar, right? So this is the weight matrix transpose times y bar. Seeing a lot of transposes in here. So what is this term? Well, this one, this is actually like a diagonal operation because it's element-wise, and so transpose would be due to the identity function, which goes away. We see that this transpose shows up in here. So if you walk through on all this, right, if you think about this now as saying, okay, I use these scalar rules to now on some examples to figure out what the vector rules should be. On this equation, what we can now start to decode what the vector rule should be is once again just a few rules, right? So you multiply a matrix going forwards, which means you multiply by the transpose of that matrix going backwards, right? So the way that you calculate y from W2 is you multiply let me take a step back up here, right? The way that you calculate y from W2 is you multiply the input by this matrix, right? Well, the way that you go backwards then is that you'd multiply y bar by the transpose of W2. The way that you calculate if you calculate z as a matrix multiplication from an input, then the way that you pull back z bar is you'd use the transpose of W1. So matrix multiplications going forwards become transposes of those matrix multiplications when going backwards. How do we know this? Well, just work out the entire, every single term scalar-wise, and you'll see that this is exactly how you do it. So you might, if you don't see it, get out a pen and paper, write this down, and do it till you see how this shows up, right? The other thing is that element-wise operations, you transpose them, but an element-wise operation is diagonal. The transpose of a diagonal matrix is the same matrix. The element-wise operations, you just, it looks almost exactly like the scalar form, except you get rid of the i's. So now if you wrote down like a generic and deep neural network, right, where you have I being the layer functions, right now you have all these different layers, you can get you get back the same exact backpropagation equation for a deep neural network if you think about it in this process where you use the rules that we had before of what do you do with multiple arrows, what do you do with this and that, but every single time you see a matrix, you just change it to the transpose. So, so here we say that R is calculated from W times V times BI. Then you do a matrix multiplication, then you do a nonlinearity. This is how you stack together to get a deep neural network, right? And then we do this for n layers, and then on the last layer we do an L2 norm, right? What is the backpropagation rule then? Well, then the derivative of the output with respect to itself is 1. The derivative of the last layer with respect to the output is equal to the derivative of the output with respect to itself multiplied by this partial derivative, right? That's that first term that we keep on having. Now we go back, right? The way that you calculated VI was from this equation. Well, the way that you calculate VI plus 1 or Vn was from this equation, right? So Vn minus 1 or Vn, the way that you calculated it, that last arrow was you did this thing. So first thing going backwards is we're going to figure out, okay, let's go backwards for how we calculated Vn. This was due to we get Vn from R, and we get it from R by just doing this element-wise nonlinearity. And so we just we do it's going to be the partial derivative of the output with respect to or the partial derivative of this function with respect to vi bar, the output of this function, right? So now that we know how to get v's from r's and we know how to backpropagate that step as well, how do we backpropagate the step that is calculating r's from w's, v's, and b's? Well, the way that you do that is you say, I'm going to have r bar show up in this equation, right? So I'm going to have that wi bar is going to be equal to, well, if you do it out scalar-wise, you'll see that you get almost exactly the same thing as the scalar-wise, except the partial derivative terms that you would have had, you just transpose all of those partial derivative terms, right? So in some sense, this equation, the reason why you don't see a transpose showing up here is because it was element-wise. This equation was element-wise. So if things are element-wise, you don't have a transpose, but for every other thing, you put in a transpose. Okay. And this is backpropagation of a general deep neural network thought of as a rule-based process on how to do backpropagation on a computational graph of an arbitrary program. That is probably a very quick explanation of it, and so you'll want to probably do things by hand, like get out a sheet of paper and do these computations until it makes sense. So this is the traditional way that people have kind of taught what reverse mode accumulation or reverse mode automatic differentiation is. By looking at how the chain rule works, by moving back on computational graphs, and I've shown you a few different ways to interpret what's going on with it, right? But now I want to give you a completely different interpretation. And the completely different interpretation is that reverse mode accumulation or reverse mode AD is all about vector Jacobian products. Okay? So, right, think about it like this, right? So you can write down a program as steps of steps of steps. But as I mentioned earlier, steps of steps of steps is another way of just saying, well, I composed a function on top of a function on top of a function on top of a function. right? So mathematically, let's write down what we're trying to do as our whole function is just L different composed functions, right? So what we have is we have f of x. Well, this function f is equal to whatever our last function is, right? So this last thing that we wanted to do, it's a function that's called on top of uh, it's a function that's called on top of the function that computed its inputs, right? Um, so like for the neural network, the last layer uses as the input the function for the layer before it, which uses the function for the layer before it. We're just going to write down the entire function as just a composition of all of those things together. So that's what I mean by this notation. Um, f the function that computes the output, or f being a program at this point, right, is actually just a composition of a bunch of more elementary steps. So if we think about the function f as just something that is a bunch of elementary functions f, what is f prime, right? F prime as the Jacobian, right? So the Jacobian of f, we can also write this as j. This is going to be by the chain rule, it's the Jacobian of L multiplied by the Jacobian of L minus 1 multiplied by L dots multiplied by the Jacobian of the first one. Right. So this is another way of writing the chain rule, right? Because we have essentially f f of x equals f L of x, or fl of fl minus 1 of dot 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 of f1 of x, right? Like this is what composition means. And so if you're to write down the derivative, the Jacobian, f prime of x is equal to fl of fl of this thing, or the Jacobian, or the derivative is fl prime of this thing multiplied by fl prime fl prime of well, fl prime of what was inside of this, and you have this chain rule, right, of dot 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 dot, where you have some gigantic term due to L f, well, the way to write this is that this is the let me use a different notation here. Let me say that fi of x. Let me say that fi of x is this term, right? So that way I don't have to like show the whole composition, right? So this is L prime, or this is, you calculate all the things before it and you take the derivative of just this last function. You calculate all the things before it and you take the derivative of just this last function. You calculate all the things before it and you take the derivative of this last function, right? So this is the chain rule, right? Going all the way down to dot 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 f1 of x prime. But what this means is that if you have a function which is a composition of many different functions, the Jacobian of that function is just the multiplication of all of its Jacobians. That is another way of the chain rule. That the chain rule is the Jacobian of a composed set of functions is the multiplication of all the Jacobians. And if you think about the computations that we did before in that light, that's another way of thinking about this, right? That the Jacobian of f with respect to t is, you just compose the derivative of f and the derivative of this function f. Well, what is its Jacobian? Right? You just multiply its Jacobian there. You keep on multiplying Jacobian, Jacobian, Jacobian. So this is just another way of writing down what we did. And forward mode automatic differentiation. So forward mode automatic differentiation, remember all it was doing, like what it was doing at its core, was calculating Jacobian vector products. It was doing Jacobian times vectors. And the way that it was doing Jacobian vector products was it would, dual numbers would calculate the Jacobian vector product of one step of the program, then the next step of the program, right? If you think about it, right, the way that we did dual numbers is that we said, if you had a function f, it will do Jacobian vector products on f. And so then when we have, g of f, well, then it does Jacobian vector products to calculate the derivative, It does the Jacobian vector products to calculate the derivative with respect to f, and then it calculates the derivative with respect to g. A way of thinking about what forward mononomial differentiation did there is that you did the calculation of the Jacobian vector product by splitting the function into JL, JL minus 1, dot, 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 JV, J1V, right? And every single step of dual number arithmetic is just doing a Jacobian vector product. And so it does a Jacobian vector product for the first function that shows up in your program, and then it uses the output of that as to do the Jacobian vector product in the second step of your program, and it iteratively just does a bunch of Jacobian vector products to get the Jacobian vector product of the full program. And why does that work? Well, because J is equal to the multiplication of Jacobians, and so what we just used here is just that, JV is equal to JL through JV like this, and we just put the parentheses in one spot, right? So that way we do, the way that we're pushing forward the derivative with the forward mononomial differentiation is we do this calculation, and we do J2 times the output of it, and J3 times the output of it. But if you start to look at this though, right, you can put those parentheses anywhere. So what is reverse mode accumulation doing with respect to this, right? So forward mode automatic differentiation is doing vector Jacobian products going forwards, doing essentially, the from the right, continually multiplying the next Jacobian until you get all the way through the function, and what it outputs is the Jacobian vector product or the directional derivative of the program with respect to the input. Remember, those two things are equivalent. So what is reverse mode AD doing, right? And if you think about it like this, what it's doing is it's just put the parentheses in a different spot. But it also did one little tricky thing, right? So what reverse mode AD is doing, right? So we think about the calculations that we did before, right? We have dy dx. Let's say we have y is a function of x, which is a function of a, right? And we also have it as a function of a here, right? So what we have done with this computation graph, right? We'd say that dy dx equals dy dA, dA dx. Oh, sorry, this is other way around. So we have y as a function of a and of a of x. Sorry. So yeah, so we have y as a function of a, which is a function of x. And so what we were doing in the calculations above, right? All those things were we'd say, dy dx equals dy dA, dA dx first accumulate, right? What we showed by doing everything with scalars is that what you actually get out of this is that this term right here is actually going to be the Jacobian transpose evaluated at the forward point. Why is it the Jacobian transpose? Well, let's look at the linear operation, right? When the operation is linear, the term that shows up here is the linear operator transpose, right? So what is the Jacobian of a matrix multiplication? It is the matrix, right? So what we did was we just transposed the Jacobian of this function, and everything locally acts like a Jacobian. And so everything locally acts like a linear function of the Jacobian, right? Everything locally acts like it's a matrix multiplication against the Jacobian. And so you can think about all these rules as really just, you calculate the Jacobian, you take that matrix, you transpose it, and that's the thing that you push backwards. That's why this transpose is really key, and it shows up everywhere. So another way of thinking about this computation then is that what we're doing with reverse mode accumulation is that we're calculating Jacobian transpose times a vector, right? And how are we doing a Jacobian transpose times a vector? Well, we're looking at what is J transpose. It is JL, it is JL, JL minus 1, L dots. J1 transpose times a vector. Now the transpose of a multiplication of matrices, it flips the order, right? So then when we have J1, so this is going to be J1 transpose, L dots, And then the last things on the right here is going to be JL minus 1 transpose, JL transpose times the vector, right? And so now what we see reverse mode automatic accumulation is doing is if it's calculating this Jacobian transpose vector at every single step of the computation, which is essentially what it means is it's doing the Jacobian transpose vector of the last term, and then it is doing the term, then it's doing the term before that, right? And why did it switch directions? Well, because when you transpose linear operations, then you actually change the direction or the directionality of that multiplication, right? And then we L dots this here, we L dots this here, and then the last term that we do the multiplication of is the first function's Jacobian transpose, right? So if you go back to this derivation and you really understand what we derived, what is actually going on is we go forwards, and then what we're doing is we're pushing back at each step, we're pushing back the Jacobian transpose of that step multiplied by the bar, and that bar is this vector v, or this previous multiplication, right? So we're pulling back by Jacobian transposes at each of these steps, right? And we can see it right here because when you omit a linear function, its Jacobian is just the matrix that you multiply it by. And so we see that what we're actually pulling back by is the transposes of our Jacobians, the transposes of our linear function. But what this also means is that, while forward mode automatic differentiation, what it was calculating was always Jacobian vector products, right? It was doing Jacobian vector products of Jacobian vector products of Jacobian vector products, and what that spits out at the end of your program is a Jacobian vector product of the composition of all functions. What reverse mode AD is doing is that it's doing the Jacobian transpose times a vector, and it's doing that at every single step in reverse. And what you get out is the Jacobian vector transpose of the composition of all your programs. Another way that this is commonly written is that if you take the transpose of this operation, VTJ, right? This is also calculated. This is just the transpose of VTV transpose, right? So you can either think about it as calculating the vector, you transpose a vector, you multiply it to your Jacobian, or you take the transpose of your Jacobian, multiplying it by a vector. What reverse mode AD is doing is just naturally doing this, right? So okay, how do we relate this back to forward mode AD then, right? So with forward mode AD, when we wanted to calculate full Jacobians, what we did was we noted that Jacobian times E1, right, where E1 is equal to a vector which is where E1 is equal to this vector which is like 1, 0, 0, v dots 0, right? We noted that if you did this, like a Jacobian times the vector E1, what you get out is J1, or the first column of the Jacobian, right? So when you put these elementary vectors in to this whole process, you get columns of Jacobian that come out. And so you can think about forward mode automatic differentiation as being something where you're always doing Jacobian vector products. You're picking, and whenever you want to use it to calculate Jacobians, you're starting out by saying that my input vector v is equal to this elementary vector. I push this through my whole program, doing Jacobian vector products the whole way, and the output of it is the first column Jacobian, right? What is reverse accumulation doing? Well, reverse accumulation is saying, well, you pick a vector v, and now what it's going to calculate is well, what is J transpose times E1? Well, J transpose times E1 is equal to you transpose the matrix and then you take the first column of it. So what is the first column of the transpose of the matrix? This is the first row of the Jacobian. So while forward mode automatic differentiation calculates one column of a Jacobian when you put in E1, what reverse mode automatic differentiation is you stick in V as E1, and then what will output is the column of the Jacobian. There's one last step missing, right? So how does this whole thing about vector Jacobian products, how does any of that relate to what I've defined here as how reverse mode automatic differentiation works? Okay? And the key is this last term, right? This L1, this L bar term, which I said it sounds really fishy that I'm just kind of saying, oh, what's the derivative of the output with respect to itself? It's 1, right? Well, this thing right here, this output derivative term, right? You can justify it as the derivative with respect to itself, but this is also just what is the term that we want to calculate the gradient of, right? This is also just a v. This is a directional term, right? So what we can think about this as is we're calculating the Jacobian vector products with respect to all these different terms, where what we're doing here is we're just doing j times t times v, where v equals 1, right? We set v equals to 1. Why did we set v equals to 1? Well, there's going to be a trick in here, right? Because let's say we have a Jacobian, right? Let's say we have df dx as our full Jacobian. We write this down as a full matrix, right? So a Jacobian is this matrix, which is fraction of partial f1 partial x1, right? And we go down by partial f2 partial x1, right? So we've written a lot of Jacobians, so I'm not going to do all of this, right? So what we're doing is we're doing things with Jacobians. Now, when we're doing things with Jacobians of loss functions, right? Remember that all of our loss functions are scalar. So why do we do the so how do we change what is the Jacobian of a scalar function? Well, you just don't have extra f's, right? You just delete all these other rows. So the Jacobian of a scalar function is just a Jacobian that has multiple columns and one row, right? What happens when we multiply this by the vector of 1, 1, by the vector that is 1, 1, 1, 1, 1, then if you do this matrix vector multiplication, right? So dfx times the Jacobian vector product, where v equals all ones, what you get here is you get partial f partial x1 plus partial f partial x2 plus L dots plus partial f partial xn, which if you looked at it, like if you looked at all of our rules were if you have multiple things in the outputs that you cared about, what you'd start to do is you would add together all the derivatives. And so it just so happens that this choice of making v equals 1 is essentially making v equals 1 is the choice that will give you a computation where the output of a Jacobian vector product, or the Jacobian transpose times vector, gives you the gradient. I'm not going to do the rest of the justification here because this will be a homework problem in homework 3 to showcase that what this is doing is it outputs the gradient. So for right now, this is a way to understand it, right? That you're choosing 1 here. And by this choice of 1, what you get out of this is you get the gradient terms, which is another way of saying that if you do Jacobian transpose times vector, then if you make v equal to 1, then what magically shows up are our gradient term. So it'll be your homework problem to really work that out in more detail. But that's really the connection here, right? So reverse mode automatic differentiation gives you with just one vector Jacobian transpose, it gives you gradients. With just one, with forward mode AD, with just one vector Jacobian transpose, or sorry, with one Jacobian vector product with forward mode, what you get is a column of a Jacobian, or you get directional derivatives. With reverse mode automatic differentiation, you're always doing Jacobian transpose times vectors, and it turns out what you finish the derivation of in your homework, it turns out that the primitive of what you calculate with this when you put ones in is a gradient, right? So how would you get a gradient of this matrix with forward mode AD? Well, you use vector Jacobian products to be able to give you what each of the columns are, and then you multiply it by a vector of ones to be able to give you the gradient. But reverse mode AD, since it's doing all columns at a time, it does essentially one reverse mode AD. It could give you gradients. This comes because we think about what this thing is here, right? Like at the very beginning of the lecture, I said, when you look at gradients, where did I write that? When you look at gradients, you should be thinking about them as row vectors. Why is that the case? Well, because the row of a Jacobian is a gradient. The row of a Jacobian is a gradient. And what reverse mode automatic differentiation does is it calculates rows of Jacobians at a time. And so if you have a scalar function and you do reverse mode AD on it, then in one reverse mode AD call, you get the entire gradient vector, whereas you need n forward mode partials or n forward mode calls in order to get all the columns to build up that gradient vector. And that is the key difference. One is working column-wise, the other is working row-wise. But you can start to build an entire system for doing reverse mode automatic differentiation at a program level in a way that looks a lot like dual number arithmetic, with primitives and all that, by using this idea of Jacobian vector products, right? So what would a primitive of reverse mode AD be, right? So the primitive of forward mode AD was you define what let's say exponential function. Let's say you want to do a primitive of that for your forward mode AD. You would define how it would work on a dual number, right? But now what we need to do is we need to tell you how to do the vector transpose thing, right? And so what is the equivalent to this kind of dual number definition kind of idea, but for things with pullbacks? So if you let y equal this vector, which is the output of f with the input x, what I'm saying here is that, so let's say that f is a function that takes in a vector and outputs a vector, right? What you want your primitive to be is you want to define a function that tells you how to get the bar terms from the input from the bar terms of the output, right? Because remember, all the way for this derivation, you'll want to do it by hand so that way you understand it better. But the bar terms, or the derivative terms of the input, are given as functions of derivative terms of the output. Okay? So what the primitive is in reverse mode AD is to tell me how one step of the pullback will happen. How would you calculate these bar terms of the inputs given the bar terms of the outputs? And what this term should be for a given function, right? So remember that when we did AD, the term that shows up on this dual part because of the chain rule should be the Jacobian, right? So your primitives for the dual number calculations is you say what the primal term is and you put the Jacobian here. The primitive here for what the pullback function is it's just the Jacobian transpose times the input vector, which is y bar, right? So every single term of the pullback is going to be y bar multiplied by the Jacobian transpose of the function f. And that if you do this on the previous idea here, right? You say that what is my primitive for this function? Well, it's the Jacobian transpose times L bar. It is the Jacobian transpose, what is this function? Well, it's the Jacobian transpose times R bar. Then you could define what are my reverse mode automatic differentiating rules for how to move backwards? It's all these pullback functions. So if you go to something like chainrules.jl, if you see how the internals of a reverse mode automatic differentiation library is built, what they want you to do is that, forward mode, they always tell you to define F rules, which is how you push forward a dual number arithmetic. The way that you do reverse mode is you give it a function which tells it how to do that pullback with respect to the y bar comes out of it. So if that is really quick, we'll be going into a lot more detail in the next lecture, showing how to do this specifically for ODEs. But this really starts to build up how reverse mode relates back to forward mode, right? So this reverse propagation thing is all about doing vector Jacobian products, and vector Jacobian products with respect to elementary vectors is giving me rows of Jacobians, and rows of Jacobians are gradients. And that's why you hear about reverse mode AD for training and parameter estimation problems, because you're always trying to calculate gradients, and reverse mode is the way to go directly to gradients. But understanding it like this gives you so much more information. So for example, everything that we were doing was with inputs where you were saying we're starting with 1, we pull it backwards. You don't have to, right? You can seed it with other inputs, right? So with forward mode AD, we seeded it with other directional derivatives. Here we can seed it with other Jacobian transposes, and we can calculate other terms which are mixtures of gradients. It seems like a really odd quantity, right? Like, how many times would you actually want to calculate JTV terms other than using it for this specific trick to give gradients? That will show up in the next lecture, right? So we can choose one as our input, and what comes out is a gradient. But we'll see that if you ever have this weird quantity, that a Jacobian transpose times a vector, if that ever shows up in a computation, a really fast way to compute it is to do reverse mode AD, where you take that one and you replace it with the input vector v, and you do you do back propagation starting from v, and that will calculate a Jacobian vector product or a Jacobian transpose times a vector. But then this means that all of the stuff that we did with sparse forward would also apply to reverse, right? Because it's all about building Jacobians one row at a time. And so you can take the transpose of the Jacobian, look at the color space of the transpose. All the same rules can apply to do, you can build full Jacobians of programs with rows at a time, mixing, doing multiple row computations at a time if you don't have a non-zero in the same vectors. So you can really start to see how you can build up full, all these things that we're doing with Jacobians and column-wise, you can now do on the transpose of the Jacobian. That's how you get the same sparse for reverse mode and everything as just row-wise operation. So I just want to end with a few notes here, right? That, for example, mixed mode operation is something that is immediately available from this idea, right? So there's combinatorially different ways to put these parameters, right? In one way we put the parentheses. In one way we're doing the parentheses so that way we're pulling everything backwards every single step, right? We're multiplying from the right to the left. In the other case, we're multiplying from the left to the right. You can also do mixed mode AD, where you multiply from the left to the right, and then you multiply from the right to the left, and you mix in the middle, right? So there are ways to be able to do not just forward or reverse mode. You're actually mixing forward and reverse mode by essentially doing the computations from both sides. And this is actually where we start to get Hessian computation, right? So remember that the fast ways to compute Hessians then directly come out of this, because remember that the Jacobian of the gradient is the Jacobian of the gradient is the Hessian, right? So let's say we want to compute a Hessian times a vector. Well, a Hessian times a vector is the Jacobian, so it's the Jacobian of the gradient calculation. So let's go back to the cost function. So dCdP, it's Jacobian times this vector, right? So how could you do this? Well, you use reverse mode AD to calculate the gradient in one step, but you do forward mode AD over the reverse mode AD to calculate the vector Jacobian product, and that actually gives you a way to do the Hessian vector product without ever building the Hessian matrix. If you look back all the way at the beginning, here, the only thing that you need to do in order to do Newton's method is you do a Hessian, you need to do the Hessian inverse times the matrix. Well, remember that from the stiff ODE lecture, that the way that you can do this inverse process, you can do it by only doing multiplications of this matrix times the vector, right? And so one way to be able to do optimization without building your Hessian is by doing forward mode over reverse mode, where your reverse mode gives you a gradient, your forward mode gives you a Hessian vector product, and the Hessian vector product is used to build a Krylov subspace to solve that linear system, to do Newton's method, et cetera, et cetera. So this has been a very quick ending here. I know that this is very quick, but I want to just kind of use this to prime you for this next lecture, where we're going to go into more detail about using this vector Jacobian transpose and really flesh out this idea. But this is what reverse mode AD. Go back through this lecture a few times. Do this computation by hand, right? Really understand it by hand. Really understand how it gets to become something like a Jacobian transpose vector. And what we'll do next time is we'll start to look at what if this program is not just a program with finite number of steps? What if this program is solve a nonlinear system? What if this program is solve an ordinary differential equation? What is the primitive of the pullback, or the what we call the adjoint equation? What is the reverse mode automatic differentiation through Newton's method? What is the reverse mode automatic differentiation through an ODE solver? And once you start to do more of these examples, I think you'll start to get more of a hang of how all these terms are equivalent and how Jacobian rows start to factor into this whole problem.